Good morning everybody. So we were in the last couple of lectures we were we have introduced many locally convex topological spaces, and we were one of them was Cm of omega, the set of all functions which are sometimes differentiable, and on Cm for each fixed m we have given a family of semi-norms which makes the topological locally convex topological spaces a family of semi-norms. Now we will go to C infinity of omega. C infinity of omega is easy. What you have to do is that you take all the semi-norms Pm and M also vary, and collect that double family of sequences. So, for on C infinity, because we have to take care of all the derivatives, because we cannot take supremum all in one topology, one semi-norm. So, you have M equal to, so we are going to vary all the semi-norm 1, 2, 3 etc., and also j equal to. So, earlier we have defined Cm of omega with Pj, but then that Pj, the family of semi-norm, depends on M. So, we are giving a indexing with respect to M as well. Okay, that is all we are doing, j equal to 1, 2, 3 etc. So, you define Pmj, a double family. Okay. Pmj of phi is equal to, for as M varies, supremum of modulus of d alpha of phi x, d alpha of phi x, where x is in kj. What is kj? Just recall kj and mod alpha less than or equal to m. So, what is kj? Kj is compact sets. Once more I am repeating, kj is an increasing family. Okay, kj plus 1. So, there is a variation with respect to. So, this p equal to Pmj, both sequences Pmj for m comma j, variation with respect to that, and with C infinity of omega with this p is a locally convex topological vector space, generates at a locally convex topological linear space. Okay, that defines you the topology. So, we have all Cm's and C infinity, and what is the convergence? Convergence under this topology we have introduced generally, but it is better to write for each particular one. Phi L converges to phi in C infinity of omega if and only if d power alpha of phi L converges to d power alpha of phi uniformly on compact sets for all alpha. So, that is it. For in Cm it is uniformly on compact sets for all mod alpha less than or equal to. With this you have all the inclusions. So, you have your C infinity of omega, continuous inclusions, all these spaces. So, you have your Cm plus 1 of omega that contained in Cm of omega and is contained in end of it C naught of omega, that is same of C of omega. Okay. So, you have all these inclusions immediately. So, just a small example you can immediately see, and then we go to the topology on the. So, look at this kind of I want to introduce some phi L. Okay, an example, phi L is equal to 1 over L if mod x less than or equal to L and equal to 0 mod x greater than or equal to 2 L, and smooth here in the other region. C infinity. You can choose that like a C infinity of omega. Okay. You can immediately see that this goes to 0 in C infinity of omega as L tends to infinity. That is very easy to see. It is not, it is right. So, you have minus 2L here, minus L here, L, 2L. So, it comes down as L tends to infinity, it becomes smaller and smaller, and then here it is 0, but in between it can be smoothly, it can be anything. You see, only thing you need smoothness, okay, can be. So, you can see that this goes to, because any compact set you can make L large enough, so that it will be less than or equal to 1 by L and you get uniformity. But then field does not goes to 0, does not converge, okay, field may not converge uniformly, may not converge uniformly in R, you see, point wise. Uniform, so field may not converge just to 0 uniformly in R2. Because of that minus L to L, it can go bigger and bigger, so you do not get that one. So, with that, now we will have the main space, our test function spaces. This is the space which we will be using all the time, function spaces. So, that is two spaces, one is CCM. What is CCM? CCM is a set of all F in Cm of omega with the support of F is compact, F compact. This compact set need not be fixed. For a fixed compact set, you already studied Cm of omega k. Okay, we will be using that. So, you have to be careful all the notations now, and this is for m equal to including 0, 1, 2, etc. Okay. M equal to 0, 1, 2, etc. and also m equal to infinity. So, notations are common here. Okay. So, we have all that. Okay. So, this is not that trivial. This is not that trivial, because as I said, our main idea, if you want to have a complete space, you have to somehow incorporate everything, all the knowledge of that in the topology. So, you have seen that if when you go to CC infinity of omega, how to incorporate all the derivatives. Now, you have the compactness property somehow, fixed compactness property, but that compact is not a fixed thing. If it is a fixed compact set, no problem, you already see it, okay, Cm of omega k, then it will be immediate norm there. But then, so what we are going to do is that an inductive limit topology. Limit topology. But I want to remark interesting remark here. This space is somewhat, in another way you can define a non-linear space. You can actually make it on CCM. If phi is in CCM, of course, you can actually make it a CCM. So, CCM, then phi has a compact support. So, each fixed phi you have a compact support. So, because of that, even though omega is open, the norm phi in m omega is finite, you see. If it is C infinity Cm of omega, that is not true, but this is finite, and hence, and this is also a norm phi m omega is a norm, because norm phi equal to 0 will imply m equal to 0, because it has a compact support, is a norm on omega. Therefore, if you take this generates a topology, okay, this is a norm generates a topology, generates a topology. So, you see, so this is slightly looks like better than, easier than your just Cm of omega, and also also you can take all these phi m of omega, m omega, m varying, m equal to 0, 1, 2, 3 will give a topology locally convex, everything is nice, locally convex topology on C infinity of C infinity of omega. So, you are immediately getting a topology with the same node. So, what is in fact the earlier topologies are all metrizable. If you have a topologies are generated by a family of semi-norms, you can use that to construct a metric. This also get a metrizable topology. So, but what is lacking is that under this topology, under this you have to understand why we want to go very specific topology. Okay. Under this topology, CCM infinity or even CCM of omega are not complete. Okay. Okay. Probably you can cook up examples or we may do exercises at later stage. Okay. So, that is why we need to have some what are called so probably there is an exercise, maybe I will skip the exercise and we will do exercise in the exercise section. Okay. During assignments we will give you the example. So, now we will go to a general notion of inductive limit topology. That is why we have to find another topology which makes it complete, but the only small price we every other property you get it, but the small price we pay for this topology is not metrizable, which you are, but that does not affect, but the sequence convergence etc. we get nicely. So, you get lack of metrizability, but completeness is much more important for us. So, let xi I equal to 1, 2, 3 be a family of topological locally convex, everything is locally convex for us. So, even if I do not mention it, it is locally convex topological spaces, these are all independent such that you have an inclusion. Xi can be, need not be an identity map, but if xi is a subset of I plus x topological space identity, otherwise you can embed it in a continuous fashion. The other way means you have a, you can put your xi's in xi plus 1, okay, continuously. Okay. So, that means that is you can define. So, you can but we consider only one. In our case it is actually a subspace. Okay. Xi there is going to xi plus 1 is continuous, that is what I said. Okay. So, let x equal to union of xi, okay, equal to 1 to infinity. Then the definition can define the inductive limit topology. Inductive limit topology is the finest topology, is the finest topology. Topology again I said that locally convex on X such that xi going to x is, in other words, okay, is continuous. So, give a topology on X so that this embedding continuous, that is xi embedded in X continuously, okay. And this should happen for all I equal to 1 to etc. Okay. In fact, you can get a local neighborhood system in the following way. Local neighborhood system you can give on X. How do you give that one? You on X. So, you take all the open sets, open neighborhoods U of the form. So, you take open neighborhoods of Ui, where Ui open in Xi, okay, and then you take its union I equal to 1 to infinity. Ui's are convex, but this not be convex. So, you take the convex hull, okay, of that. In that way you can get a locally convex. For more details you can refer the books, and then you run over all possible such things, and then you get a, this is a open means convex neighborhood of 0. So, if you want that thing neighborhood of 0, so you run over all possibilities and then you get a neighborhood system. You can get that by taking the all the convex neighborhoods, okay. So, I can just this is a trivial theorem, but if you want you can understand the neighborhood system properly and then you can do that. So, this is important. If T from, this is what eventually we will be doing it in CC infinity of omega. So, T from continuity, understanding the continuity of the linear mappings, okay. T from X to R is continuous if and only if. So, one T is there. So, you can restrict T to Xi, that is a mapping from Xi to R is continuous. So, you have to just write down the continuity for all I, okay. That is how you do that. So, these theorems are just follows from the topology the way you have defined. Now, we will define with that locally convex topological linear space, what do you call it, both CCM of omega. Later I will give you another notation, CC infinity of omega, okay. Now, it is just define appropriate Xi's and U. So, let me give you a start with a notation, new notation, K subset of omega compact, then I define dk. So, of m is this is the say dk m of omega so same I think Cm of this is the notation already given, set of all Cm functions with compact supporting that one. And for this you have your topology Pm of phi, because it is a compact support. So, the norm phi, this is how we already defined K. So, that is the same as norm phi at m omega, you define that one. So, including m equal to infinity, not m 0, 1 etc. and also infinity, okay. So, you have m equal to infinity, it is dk infinity of omega, okay. So, for each one you can do that one. So, let us go to the main thing of defining that one. So, you define x is equal to now CCM. So, m fix it, okay. I am fixing m for the time. CCM of omega, that is equal to union of CC m of no, that one dkj. So, you have that kjs, you call it dkj of omega. So, you get ccm of omega is same as this one, you see it fills up everything kj. So, this is only m differentiable functions with support in kj. So, every k can be put it inside a kj, because kj is going to infinity, you can kj is going to omega. Okay. So, and this is going to your be xi. Okay. So, you already have a topology on ccm of omega. So, this is union of xi, you see I equal to. So, we have already the topology, that is all the spaces. So, xi is already given by the locally convex topological spaces. These are all locally convex topological linear space. So, you have, so it gives you, so this gives you an inductive limit topology by that one, inductive limit topology. Okay. And I want to maybe make one more. In this theorem I did not write all the part, there is something more to that theorem. Okay. See, these xi's are very general. So, but if xi is closed, because this is an additional thing, closed in xi plus 1 need not be, because it is completely different, and xi plus 1 induces the same topology on xi, then x induces the same topology, induces the same topology on x, on xi. This is the first part and this is the second part of that theorem. Okay. So, you have the, if that additional assumptions of xi's are closed, you get a little more about it. And so, these are closed, you know that, because these topologies are understood well, these are closed, and further dkj, careful which one I am varying, okay. M I am fixing it. So, this is always contained in, because kj is bigger. So, if the support is in kj, support it is also in kj plus 1, and the same topology, it gives you the same topology. So, that induces the same topology. Hence, the CCM induce the same topology on Tkj of M. Okay. So, you have these spaces. So, this is the thing, important thing you have to follow it. Okay. With that, so we give a notation. So, x or CCM omega with the above topology, is denoted by dm, okay, dm of omega. So, have this notation. So, dm of omega is used, it is CCM, but not with the, because we could define earlier also some topologies which are not complete, and you will be able to define various topologies. So, with this inductive limit topology, in particular we give one more notation, particular, if m equal to infinity with the topology Cc infinity of omega, which is denoted by d infinity of omega, which we denote by d omega. So, this is the space we will be working on. So, CC and infinity of omega with this topology is your d omega. Okay. So, so maybe with this probably I have some more things. Yeah, I have a few more minutes and maybe I will write the convergence. So, what is convergence? Convergence, because convergence eventually you have to know. So, phi L converges to 0, we say phi L converges to phi in d omega if there exists a compact set careful now here. When I say phi L converges to phi in C infinity of omega, there is no existence of a compact set. It says only phi L converges to phi uniformly in every compact sets. But here we are demanding the additional, we are in the definition, it is not really a definition, it comes from the topology, it is already defined. So, this comes from the topology. There exists a compact set K such that the support of all phi L contained in K for all L, that is important. Okay. And d power alpha of phi L converges to d power alpha of phi uniformly. You can say either in K, because outside it is 0, or in omega, it is immaterial now, because if it converges uniformly in K, it converges thing, because there is a uniform K. Uniformly in omega, or K, both are same, for all mod alpha, for all alpha. Okay. Cm means if it is in Cm, then it means it is for all mod alpha less than or equal to m. So, that is the only variation you have to make. So, this is very, very important. Okay. Very, very important, this convergence of K. Okay. So, earlier we have given an example where phi L converges to 0 in C infinity of omega. That will not converge because that does not have a uniform compact set, because the support is in minus 2L to 2L, the example which I have given. But now you see that will not, as L tends to infinity, the supports are going to infinity. So, that is a difference where certain sequences converges in d omega and some other sequences may not converge. Okay. One more remark, with a couple of remarks, we will probably end with that, with the preliminaries remark. I am going to define one more topology. Observe another thing, this you can see that. Observe your d omega contained in dm of omega. Here m I am varying. See, earlier the variations were, so to be carefully see that here the dkj of m is fixed and dkj of m is contained in dkj plus, is not, is the same thing. And topology defined is a finest topology on X for which the inclusions are there. Now, this is for you can, this is a fact which you can derive, d omega contained in dm of omega, the way it is defined, the inductive limit topology is defined. The d omega of course contained in dm of omega, but that inclusion, the identity mapping is continuous. Observe. Okay. The important thing, this need not be the final, this need not be the coarsest topology. I will tell you what I think. That means this topology, inductive limit topology defined on Cc infinity of omega given by the inductive limit topology makes this inclusions d omega to dm of omega continuous, but then it may not be the smallest topology, coarsest topology. So, we can define another topology, can define in fact this need not be the thing at this stage I wrote it, but the end of it you can see that is not really, it is not. Okay. Can define another topology on C infinity of omega. So, when I am defining a different topology I use C infinity of omega, I do not use d omega for anything else. The moment d omega is done, the topology on C infinity is done. Another topology C and omega, which is the coarsest topology, which is the coarsest topology such that d omega 2 t contained in dm continuously continuous. Okay. And this is denoted by, this is denoted by df of omega. You will see f representing, when you study distributions you will see that f meet finite. So, the notation f is for finite. When you look at the dual, d prime gives you bigger dual than your df. So, in that sense you can actually say that in that sense you can say that d of omega contained in df of omega. So, you see both d and df omega as vector spaces is the same. Okay. They are the same vector spaces C infinity of omega, but the topology makes them, this is smaller. That smallness you will see when it looks at its when its linear operators on that spaces. Okay. And so, with a couple of final remarks, these are all remarks we think which are already made. dm d are local, once again repeating, okay, locally convex topological vector spaces, but they are not metrizable. As I said, this is the only small thing. Okay. And on the other hand, you have defined Cm, C infinity are metrizable in locally convex. So, you have both, you see the diagram, if you remember the earlier the first diagram of topological space, metrizable locally convex topological vector spaces. Okay. So, you have that one. So, with this I think I will stop this preliminary part and yeah. So, if anything more required for our course we will do it at that time. If there is anything, any preliminaries are missing, either we recall or we will state it to you. So, before venturing into study of distribution theory, at least you should go through, if not everything about topological spaces, some important aspects of these spaces, especially the convergence, get convergence and all that. So, one more thing, you can also have this inclusion. So, you have your inclusions d omega contained in C infinity of omega. So, these are all continuous inclusion. Here you have df of omega. So, at the end in the during the theory of distributions, you will study all this d prime, that is precisely your set of all distributions. You will here you will see the dual of this, you will get the set of all finite distributions. Then you will have C in M of dual, and then you will see the implications of all that, and then C infinity of omega dual. Okay, all this we will see when we study distributions. So, let me stop this one and we will continue with the theory of distributions from the next lecture onwards. Thank you.